Hello everyone, welcome to Civil Galaxy. I am Dr. Pruthviraj B S. Today we shall see how to analyze a continuous beam with the help of consistent deformation method. So to analyze any beam using consistent deformation method, my first step will be to find out the degree of static indeterminacy. So to find out degree of static indeterminacy, we need to know the number of reactions and the number of available equilibrium equations. So in this particular beam, we are having one vertical reaction here about point A and we are having one moment here about point A. Similarly, we are having one vertical reaction about point B and one vertical reaction about point C. So my total number of reactions are 4 and my available equilibrium equations are 2. So if I want to find out the degree of static indeterminacy, which will be equal to 2. So we are having two extra forces, or these two forces needs to be treated as the redundant forces. So in this particular continuous beam, we will consider reaction about point B and reaction about point C in the vertical direction as the redundant forces. So if we treat vertical reaction about point B and vertical reaction about point C as the redundant reaction, the same structure can be treated as a cantilever beam, which will be a determinate structure. So this is point A, this is point D, carrying a point load of 60 kilonewton. From point A, it is at a distance of 4 meters. So from B to D to B, it is having 2 meters. Similarly, this is from B to C, it is carrying a load of 20 kilonewton per meter UDL. So now I want to find out, in the step 2, we need to find out the downward deflection. The downward deflection at point B and at point C. The downward deflection about point B and point C. So since I have to find out the downward deflection at point B and point C, due to the external loading, this I will consider it as capital M. Similarly, to find out the downward deflection about point B and point C, we will use a unit load method. Since we know from unit load method, whenever we need to find out the deflection, we need to use a unit load. Similarly, if we want to find out a rotation, we will use a unit moment. So since we need to find out the deflection here, we will use a unit load. So if I take the beam here, this is point C. At point C, we will apply a unit load. This is point B, this is point D, this is point A. Distance here is, this is 4 meter, this is 2 meter and this is 6 meter. Similarly, I need to find out the downward deflection due to the applied unit load about point B. I'll apply one unit load here, 1 kilonewton about point B. This is point C, distance is 6 meters. Similarly, here this is point D, this is 2 meters, this is 4 meters, this is point A. So this downward deflection applied due to the unit moment about point C, I will consider it as small m1. Similarly, the downward deflection due to the applied unit load about point B, we will take it as small m2. So now to simplify or further analysis, we will consider a table. If we closely observe, we can see we are having three portions here, that is C to B, B to D and D to A. So we have considered three portions, and for that three portion coming in the right side direction, we have to consider the origin. So for the portion C to B, the first point or the origin point will be C. Similarly, for the portion B to D, the first point or the origin point will be B. For D to B, it will be D. So now I have to define the limit. The limit here is for the portion B to C, it is 6 meters, means the limit is here 0 to 6. Similarly, for B to D, the limit is 0 to 2. Similarly, D to A, the limit is 0 to 4. Now I have to find out the deflection or the moment due to the external loading, which we have considered it as capital M. So for this portion, if you want to consider the moment, we will take one section about this point x at a distance of x from the origin, that is x. So if we consider here, if you want moment about this point, force multiplied by perpendicular distance, force here is 20 and the distance here is x. Since it is a UDL, we have to consider this CG half rotating in the clockwise direction, creating a hogging moment, it is a negative. Similarly, for portion B to D, if you want to consider a moment about this point, we will take a section x having a distance of x here. So now we want moment about this point, force multiplied by perpendicular distance. Force here is 20 multiplied by perpendicular distance, the total distance from B to C is 6 multiplied by into, that is 6 by 2 plus x, rotating in the anti-clockwise direction, it is negative. Similarly, if I want to find out moment about this point x, this will be the distance small x. So now the total load here is force multiplied by perpendicular distance about this point, force multiplied by perpendicular distance into, which rotates anti-clockwise, which rotates clockwise, creating a hogging moment, 20 into x, force multiplied by perpendicular distance, into CG 6 by 2. So from here to here it is 2 plus 2 plus x. So now similarly, moment, if you want to find out moment due to the applied unit load about point C, we will consider one section here x acting at a distance of x here. So if I want moment about this point, force multiplied by perpendicular distance, that is minus 1 into x, rotating in the clockwise direction, creating hogging moment. Similarly, if you want to find out moment about this portion x acting at a distance of x, which will be minus 1 into 6 plus x. Similarly, if you want to find out moment about this point in this portion dA, this distance here will be x. So now, which is nothing but force multiplied by perpendicular distance is 8 plus distance about the point where we want to find out the moment is x. So now similarly, if you want to find out moment due to the applied load or applied unit load about point B, for the portion B to C, if I consider a section x here, since there is no load acting in this portion, so this moment comes out to be 0. Similarly, for the portion B to D, this is x. I want to find out moment about this point, force multiplied by perpendicular distance, which is 1 into x. Similarly, for this portion x at a distance of x, we want to find out force multiplied by perpendicular distance, that is force multiplied by perpendicular distance 2 plus x. So the flexural rigidity here is uniform. So now if I further simplify this table, we have minus 20 x square by 2. Similarly, this will be equal to minus 360 minus 120 x. Similarly, this value comes out to be minus 600 minus 120x minus 60x. So this will be minus x, minus 6 minus x, minus 8 minus x, 0, minus x, minus 2 minus x. So these are the values. So now we have to find out, the deflection about point C and also about point B. My objective is to find out the deflection about point C and about point B. So now to find out the deflection about point C, to find deflection at C, that is delta C. If you want to find out the deflection about point C, we will, from Castigliano's second theorem, we can take 0 to L, moment due to external loading and moment due to the applied unit load about point C, which will be equal to small m1 divided by EI into dx. So now I have to consider for each portion the deflection. So I have to consider the deflection about the portion CB, the portion BD and also the portion DA, which will be equal to delta C, means which will be equal to the deflection about the portion CB plus the deflection in the portion B to D, also the deflection in the portion D to A. So now if I want to find out individually all these three deflection, so deflection about point CB, which is capital M into small m1, 0 to L divided by EI into dx. So I can simplify or rewrite here is the limit is from 0 to 6. Similarly, that is minus 20x square by 2 capital M, small m1 is minus x divided by EI into dx. So now if I further simplify this, that is 0 to 6, we will be having 10x cube by EI into dx, which will be, if I take 1 by EI outside here, we will be having 10x to the power of 4 by 4. The limit is 0 to 6. 0 to 6. So now if I further go on simplifying this, my delta in the portion C to B, comes out to be 3240 by EI. This is the deflection about the point C to B. Similarly, finding out the deflection in the portion BD. Similarly, finding out the deflection in the portion BD, we can write here as the limit is from, for this portion B to D, the limit here is from 0 to 2. If I rewrite this M and small m1, we will be having 2160 plus 360x plus 720x plus 120x square by EI into dx. Similarly, this is the limit is from 0 to 2 here, that is 120x square plus 360 plus 720, 1080x plus 2160 by EI into dx. So if I take 1 by EI outside, that is 120x cube by 3 plus 1080 x square by 2 plus 2160 x, and the limit is from 0 to 2. So now the deflection in the portion B to D comes out to be 6800 by EI. So now similarly we have to find out the deflection about in the portion D to A, in the portion D to A, in the portion D to A. Limit here is 0 to 4, which will be 180 x square 180x square plus 2040x plus 4800 divided by EI into dx. So now if we take out 1 by EI outside, we will be having 180 x cube by 3 plus 2040 x square by 2 plus 4800 x. The limit here is 0 to 4. So if we further simplify, delta in the portion D to A comes out to be 39360 by A. So since we have got all the values of displacement or deflection about the portion CB, BD and DA, we can have the value of deflection about point C. So adding all these values, delta C value comes out to be 49,400 divided by EI. This is my deflection about point C. Consider it as equation number 1. Similarly, we have to find out the deflection at point at point B, which will be delta B. So the procedure is similar here. We have to find out delta B. So for delta B also we will be having the deflection about in the portion CB, deflection in the portion B to D plus deflection in the portion D to A. We have to consider this one, the moment due to external loading and moment due to the applied point load or the unit load about point B, which will be equal to M2 here. So now similarly, if you want to find out delta CB value here, that is minus 20x square by 2 multiplied by 0. So delta CB value will be equal to 0. I need to find out delta BD. I need to find out delta BD value. So delta BD value is the limit here is 0 to 2, which comes 360x plus 120x square divided by EI into dx. If we take 1 by EI outside, 360x square by 2 plus 120x cube by 3. The limit here is 0 to 2. So deflection in the portion B to D will be equal to 1040 by EI. Similarly, we have to find out the deflection about the portion D to A. Deflection in the portion D to A. The limit here is from 0 to, the limit here is 0 to 4. So capital M, this into this small m2, 0 to 4, that is 180 x square plus 960 x plus 1200 by EI into dx. Similarly, if we calculate further, we will be having, if I take 1 by EI outside, that is 180 x cube by 3 plus 960 x square by 2 plus 1200 x. Limit here is 0 to 4. So the value of deflection in the portion DA comes out to be 16320 by EI. So now, to find out deflection about point B, adding all the values which we have got here, we are going to arrive at the deflection about point B. we are going to arrive deflection about point B. So deflection point B here is 0 plus deflection about point or in the portion BD was 1040 by EI plus deflection in the portion D to A was 16320 by EI. So now deflection about point B will be equal to 17360 by EI. We'll call it as equation number 2. So now we have found out the deflection about point B and about point C, that is the downward deflection. So in the step 3, we have to find out the upward deflection at point C. That means we have to apply the redundant force about point C and we have to find out the upward deflection. For that we will consider the beam here and applying the or treating the vertical reaction at point C here as the redundant force. So this is point B, this is C, this is point D, and this is point B. The distance here is 6 meter, here it is 2 meter, here again it is 4 meter. So now this is point A. So now if I want to find out the deflection due to the upward deflection or the reaction about point C in the vertical direction, the beam undergoes a deflection in this way. So now I have to find out the deflection about this point C, where I will call it as deflection at point C here. Similarly, due to this, we will be having one deflection here also about point B. We will call it as deflection about point B also here. I will name it as YC1 and YB1. So now if I want to find out the deflection about point C here, the upward deflection, we know I want to find out the deflection here, that is YC1, which will be equal to, we know from the standard deflection equation, whenever a cantilever beam is subjected to a point load at the free end, it will be equal to WL cube by 3 EI. So here W is nothing but the reaction about point C in the vertical direction, and the length or the total distance here is 4 plus 2, 6, 6 plus 6, 12 cube divided by 3 EI. So now this comes out to be the deflection, that is YC1, I can call it as 576 reaction in the vertical direction about point C divided by EI. So this I can consider it as equation number 3. Similarly, now I want to find out the deflection here about point B. So we will apply a unit load here about point B, applying a unit load here about point B. We want to find out the deflection about point B due to the reaction about the vertical, reaction about point C here. This is A, this is B, this is C, and this is D. So now to find out the vertical or the upward deflection about point B here due to the reaction about point C, I have applied a unit load here 1 kilonewton in the upward direction. So for that YB1, to find out YB1, I will consider the limit 0 to L, capital M into small m divided by EI into dx. What is capital M here? The capital M here is the deflection due to the vertical reaction about point C in the upward direction, and small m is the deflection in the upward direction due to the applied unit load. So for that we will take each portion again. So taking or considering each portion, each portion. That is, if I consider for the first portion, since we are having 3 portion here, the portion name I will write it. The portion we are having here is CB. Similarly, B to D and D to A. So for these 3 portion, I have to find out the capital M and the small m. Origin I know, limits we know. Similarly, I have to find out capital M and small m and flexural rigidity. Similarly, for origin, here it is C, this is B and this is D. The limit here will be 0 to 6, 0 to 2 and 0 to 4. Similarly, I want to find out moment about for this portion. So if I want to find out moment about this portion here, that is x at a distance of x, force multiplied by, here it is force multiplied by perpendicular distance rotating in the anti-clockwise direction, creating a sagging moment which will be reaction about point C in the vertical direction multiplied by perpendicular distance rotating in the anti-clockwise direction, creating sagging moment is positive. Similarly, if we write the small m, that is moment due to the applied unit load about point B about this portion, since there is no loading here, this will be equal to 0. Similarly, we want to find out moment about this portion at a distance of x, force multiplied by perpendicular distance. Force here is reaction about point C in the vertical direction multiplied by 6 plus x. Similarly, want to find out the moment about this point at a distance of x, force multiplied by perpendicular distance, here it will be 1, here it will be 1 into x. Similarly, for the last portion here, if you want to find out the moment about this point or portion here, x. So, about this point, force multiplied by perpendicular distance, force here is reaction about point C in the vertical direction into 8 plus x. Similarly, finding out moment about this point or in this portion, x at a distance of x here, force multiplied by perpendicular distance, here the distance is 4 meters, this is 2 meters and this is 6 meters. So about this point, force multiplied by perpendicular distance will be 1 into 2 plus x. Flexural rigidity is same throughout, EI. So now, if you want to find out the deflection about point B, that is YB1, for YB1, we have to add the deflection for all these 3 portions, that is deflection about C to B plus deflection in the portion B to D plus deflection in the portion D to A. So now, finding out the deflection for each portion, applying the Castiglione's second theorem, that is 0 to L m into small m EI into dx for each portion. So the deflection about point CB in the first one, that is this multiplied by this one, will be equal to 0 directly, since the moment in the portion CB due to the applied unit load is 0, will be 0. Similarly, I will write the answer directly here. Deflection in the portion BD, if we calculate this one by applying the formula, we will be having 14.67 vertical reaction in the point C divided by EI. Similarly, deflection about point D to A will be equal to 165.33 vertical reaction about point C by EI. So now, if you want to find out the deflection about point B, that is YB1, YB1. So here YB1 is equal to delta CB plus delta BD plus delta DA, which is delta CB is 0 and the delta BD is 14.67 by EI, reaction about C in the vertical direction. Similarly, 165.33 RCV by EI. So now we will be having YB1 will be having 180 reaction about point C in the vertical direction divided by EI. So this I can call it as equation number 4. So now similarly I have to find out, or treating the vertical reaction about point B as the redundant force in the step 4. In the step 4 we will treat the vertical reaction about point B here as the redundant force. If we treat the vertical reaction about point B here as the redundant force, this is A, this is D, and this is C, this is 6 meter, this is 2 meter, this is 4 meter. So the deflection will be in this fashion. So now I want to find out the deflection here about point B, where I can call this deflection as YB2 and this deflection here about point C as YC2. So now to find out the deflection about this point YB2, we know whenever a point load is subjected, a cantilever beam is subjected to a point load at the center, we are having the formula WA cube by 3EI. So here W can be considered as reaction about point B in the vertical direction. The distance here is 6 cube divided by 3EI, which comes out to be 72 reaction at B in the vertical direction divided by EI. So this we can consider it as equation number 5. So now similarly we want to find out the deflection about point C due to the applied unit load here. Considering the point B as the redundant reaction, we are having a deflection here at point C. We will take it as deflection about point C. So which will be equal to, so we have to take for this point C here, we will take the deflection about point B2 plus the deflection here about the point C. So for that, the deflection about point B here we have got, that is WA cube by 3 EI plus for the deflection about point C here due to the redundant reaction about point B will be WA square B by 2 EI. Now simplifying these values here, W can be taken as reaction about point B in the vertical direction. A is nothing but the distance here. This is A and this will be B. So A here is 6 cube divided by 3 EI plus W, that is reaction about point B in the vertical direction. A is 6 square multiplied by this B. This is 6 divided by 2 EI. So now if I want to find out the reaction or the deflection about point C, we are going to get, after simplification, 180 reaction about point B in the vertical direction by EI. Let us take it as equation number. Let us take it as equation number 6. Let us take it as equation. In the step 4, further applying the compatibility equation or according to consistent deformation method, according to consistent deformation method, we have to see, our objective is to find out the deflection at point C and the deflection about point B. So deflection at point C will be equal to the deflection at point C 1 plus deflection at point C 2. So which will be equal to deflection at point C, we know, that is 49400 by EI is equal to reaction at point B in the vertical, reaction about point C in the vertical direction, reaction at point C in the vertical direction, 576 by EI, that is YC1 value, plus similarly YC2 value we have got reaction about point B in the vertical direction into 180 by EI. If I simplify, we are going to get an equation, that is 180 RBV plus 576 RCV, which will be equal to 49,400. This we will call it as equation number 7. Similarly, find out deflection about point B, that is YB1 plus YB2. YB1 value is 180 reaction about point C in the vertical direction by EI plus 72 vertical reaction about point B divided by EI. So delta B will be equal to delta B value we have. Delta B value is 17360 by EI. So further simplification, we get the equation 72 reaction about point B V 180 RCV is equal to 17360 by 17360. This we can call it as equation number 8. So solving equation number, so now further solving equation 7 and 8, solving equation 7 and 8, we get the value of reaction about point B in the vertical direction. We have got 122.06 kilonewton. Similarly, reaction about point C in the vertical direction, we have got 47.6 kilonewton. So here my objective is to find out the unknown parameters, that is moment about point A, reaction about point A in the vertical direction, reaction about point B in the vertical direction, similarly reaction about point C in the vertical direction. So now out of these four, we have got reaction about point B in the vertical direction, reaction about point C in the vertical direction. So I am left with reaction about point A in the vertical direction. So for that we will take summation of all the vertical forces is equal to 0, that is reaction about point A V RBV plus RCV plus RCV, which will be equal to 60 plus 20 into 6. Upward force should be equal to the downward force. So RAV plus RBV value we have got here 122.06 plus RCV 47.6 equal to 60 plus 120. So now reaction about A in the vertical direction after simplification comes out to be 10.34 kilonewton. So if you want to cross check this one, we will calculate the total load. Total load is nothing but 60 plus 20 into 6, that is 120. The total load is 180 kilonewton. So now reaction about A is 10.34, reaction about point B is 122.06 kilonewton, reaction about point C in the vertical direction is 47.60 kilonewton. So we add all these three should be equal to the total load, that is 180 kilonewton. So now we have found reaction about A in the vertical direction also. The last we are having here is moment about A is equal to 0. If you are taking moment about A is equal to 0, sigma m is equal to 0. So moment about A can be considered as vertical. Here I want moment about this point, force multiplied by perpendicular distance, that is reaction about point C in the vertical direction multiplied by the perpendicular distance 12. Similarly here plus reaction about point B in the vertical direction multiplied by perpendicular distance 6 minus this force here 60 into 4, 60 into 4, so minus this one here 20 into 6 into this is about this point, force multiplied by perpendicular distance, load is 20 into 6 multiplied by perpendicular distance is CG, that is half, 6 by 2 plus 4 plus 2, that is 6. So now moment about point A will be equal to, so minus 16.44 kilonewton meter. So now to summarize this continuous beam with the help of consistent deformation method, we have got reaction about point A in the vertical direction 10.43 kilonewton acting in the upward direction. Similarly, reaction about point B is equal to 122.06 kilonewton acting in the upward direction. Similarly, reaction about point C in the vertical direction 47.66 kilonewton acting in the vertical direction. Similarly, moment about point A, which is minus 16.44 in the anti-clockwise direction. So similarly, we shall see few more examples related to this consistent deformation method in our coming classes. Thank you.